We begin a discussion of rate of change. Rate of change is something we're going to talk about for the rest of the semester. So this is big. And there are two rates of change that we're going to talk about today. We're going to talk about the slope, and slope and rate of change are synonyms. We're going to talk about the slope between 2 points on a function. And if you draw a line that goes through 2 points of a function, maybe I'll draw a little one over here, something like this. There is a line that hits that function at 2 places. That is called a secant line. It's a trigonometry term that we're familiar with, but that's also a line that hits a function at 2 points. And if you find the slope of that, what you found is you found the average rate of change. And that's something you'll be asked on the AP test, to find an average rate of change. And this function is continually changing as it works its way from one point to another point. Slope is negative at some points, positive at others. The average of all of those different rates of change, of all of those different slopes that this function encounters, is found by taking the slope of that secant line. Now, if we use really small intervals, not a big interval that goes from 2 points that are really far away, but points that are really close to each other, then you get closer and closer to the slope of the tangent line. Slope of the tangent line is a huge concept. But how do you find the slope of the tangent line? Well, for today, we're going to find slopes of secants using very small intervals. And the slope of a tangent line is also known as the instantaneous rate of change, not the average rate of change, not a whole bunch of different ones that when we add them all together and find the average, we've got a number. Now this is the rate of change at an instant. Let's take a look right here. Let's take this and move this over here. Now right now, this looks like a secant line, doesn't it? I am interested in finding slope of the tangent right here. Now a tangent line right here would probably look something like that, wouldn't it? Well, this secant line between the points A, f of A, x, f of x, nowhere close to that tangent line. But what if I took that point, let's try it again. What if I took that point, I can't do it, and moved it closer over here? What if I moved it maybe right there? Let's move xy over here. Let's move the second place that this line hits the graph. Let's move it right over there. Well, if I do that, that's getting closer and closer to being a secant, or to being a tangent line. But what if I move it even closer? Let's move x, f of x, right there. Well, now I got to move that line again. Boy, that's even closer to being the tangent line, isn't it? So if the points are really close to each other, then that secant, that slope of the secant and the slope of the tangent become pretty darn close to each other. So if we're going to find this instantaneous rate of change, here's how we do it. We're going to find a slope. We're going to find a slope by taking y2 minus y1, f of x minus f of a, over x minus a. Now let's just go back here. y2 minus y1 over x2 minus x1. So we're finding the slope of a secant line. However, we're going to say that we're going to take the limit as x gets really close to a, as these x values are really, really close to each other. All right, well, let's see what we can do. We want to find the equation of a tangent line. Now, the equation of a line, y equals mx plus b, y equals something, times x, plus something. Let's fill in those somethings. And the something we always fill in first is the slope. Well, I want the slope of the tangent. I want this instantaneous rate of change. And they've told me how to do that. So I'm going to take the limit as x gets close to, well, now in this case, it looks as if x is getting close to 1, isn't it? And I've got to take f of x. Well, here's f of x right here. They will give us a function, and we will say that function is x squared. Minus f of a. Well, what is the function at 1? What's the value of the function at 1? We find that right here. It's 1. Divided by x minus a. In this case, x minus 1, because we're told that we're getting close to that x value of 1. Well, now if I put a 1 into this limit, I'm going to get 0 over 0. And I think we talked about limits that were 0 over 0. One of the tools we'd pull out of our toolbox is factoring. We're going to take the limit as x approaches 1, x plus 1, x minus 1, over x minus 1. And we see that these guys factor out to be a 1. Remember, we're only getting close to 1. These aren't really 0, but they are the exact same number, and so they would factor out to give us 1. And now if x is approaching 1, well, then x plus 1 is getting pretty darn close to 2. Now we got to find the y-intercept. And to find the y-intercept, you always plug in a point. Well, this is the one point that I know is on the tangent line. Tangents only hit at one point, and they'll tell us what that one point is. So the y value equals the slope times the x value plus how much? Well, 1 equals 2 plus we got ourselves the equation of the tangent line at the point 1, 1. Now, this form right here, this was really helpful when we knew that A had a value of 1, when we were told what point we were approaching. But what if we don't know A? What if they don't specify? Well, then we're going to use a different form to find the slope of the tangent. We're going to use this form right here. And this is really helpful in finding the slope when they don't tell us what x value we're approaching. Now, one other concept that we've got to understand is what velocity is. And those of you who have taken physics probably know this. Those of you who are in physics, I don't know if you've gotten there yet, but slope of the tangent to a position time graph. If you find the slope of a position time graph, you have found velocity. If it's the slope between 2 points of a position time graph, you found an average velocity. If you find the slope at a single point of a position time graph, you found an instantaneous velocity. A velocity, slope of a position time graph. We're going to do lots of work with velocities, positions and times, accelerations, starting in this chapter. Now, an object is falling from a tall tower in Toronto. Here's the position function. This is the position time function. If we find the slope, we're going to find the velocity. So now what I'm going to do is I'm going to find the limit as h approaches 0, because we have not been told at what time to find the velocity. I've got to take f of a plus h minus f of a. Divide that all by h. So I got to put an a plus h into this function right here. I got to take the limit as h approaches 0. And if I put an a plus h in there, I get 450 minus 4.9 a plus h going in place of the t squared. There's f of a plus h minus f of a. So if I put an a into here, 450 minus 4.9 a being squared. And I got to put that in parentheses. Got to remember to subtract the whole thing and divide by h. Well, if you think that's a pain, now let's expand this thing. This is the most painful of the steps. We're going to take the limit as h approaches 0. And in this first set of parentheses up in the numerator, we have 450 minus, well, a plus h squared. If I squared a plus h, I think I'd get a squared 2ah and h squared. And I'm supposed to multiply that thing by 4.9. So I think I'm going to be, and remember, I'm subtracting this thing. So I'm going to be subtracting 4.9 a squared. I will also be subtracting 9.8 ah. I will also be subtracting 4.9 h squared. Then I've got to subtract this 450 minus 4.9 a squared, and I've got to divide that entire result by h, and that's long and involved and complicated. But do you see how we could maybe simplify this thing? Do you see where you have a 450 minus a 450, and so that's gone? Do you see how you have a minus 4.9 a squared minus negative or plus 4.9 a squared? And this entire f of a goes away. And if you think that's a coincidence, think again, because that's going to happen every single time we do one of these limits as h approaches 0. So what's left? We got the limit as h approaches 0, and I got to take this divided by h. When I do that, I get negative 9.8 a. I got to take this, which remember is being subtracted, and divide it by h. And that's going to be 4.9 h. And if h is approaching 0, if h approaches 0, I think what I'm going to get is negative 9.8 times a. Now, we don't know what a is. But whatever the value of a is, whatever x value we're approaching, whatever value of time we're approaching, to find the velocity, the instantaneous velocity, I'm just going to take negative 9.8 times that time value. So when we ask for what's the velocity at 5 seconds, well, v of 5 is going to be negative 9.8 times 5. I think we're going to get negative 49. You want v of 7? Just take negative 9.8 times 7. Oh, now what's that? 56, 63, negative 68.6, I think. Now, what's the velocity when the object hits the ground? Well, I don't know, because I don't know what the time is. I do know that the position of this thing is 450 minus 4.9 t squared. And I'm interested in when the position is on the ground. The position, the height of this object is 0. Now I can solve that equation. And what I'd like you to do right now is press pause and solve that equation. Now, you probably divided by 4.9 and took the square root, and you probably found that the time was 9.58314.8, yada, 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 a lot of numbers. Now, normally, always, when you can use your calculator in calculus, you got to be accurate to 3 decimal places. But it's your final answer that has to be accurate to 3 decimal places. And your final answer is not this time value. And so you have to use all these digits that are on your calculator. And if you want to find the velocity at that time, you will take negative 9.8 times that time, and you will come up with I'm hoping you get negative 93.914. And if you rounded that up to a 5 because it was followed by an 8, that's fine. We are accurate to 3 decimal places, and we either truncate after 3 decimal places, or if you see this 8 over here and want to turn that guy into a 5, well, you can feel free to do that. So those are the 2 acceptable answers. So definition of derivative. Okay, here's our vocabulary, whoopsie. Our vocabulary word of the semester. Oh man, you just don't want to stay, do you? Is the word derivative. Derivative means slope. Slope of a tangent. Those are synonyms. And you can either find it like this, or you can find it like this. And we'll have other ways to find it. But this is the definition of derivative. And it's found by taking limits. Now, this is just another notation. This is called f primed of a, the derivative, the slope of the tangent. F primed of a. F primed of a. If I know what a is, I'm probably going to use this form. If I don't know what a is, this is a more convenient form. And that concludes our discussion of rate of change and our understanding of the terms average rate of change and instantaneous rate of change as the slope of the secant and slope of the tangent.